All right, so we're going to review for Unit 4. Okay, remember that this started kind of well before Christmas, okay, with all the simple harmonic motion stuff, with the, the pendulum and the mass on a spring, and then Hooke's law and conservation of energy and all that. That's all still part of this unit. It kind of seems like it's a different thing, but it's, okay, it's really the first half. All right, so the first thing that we covered in this unit was simple harmonic motion, okay? And we looked at what it means to move with simple harmonic motion, okay? And we looked at the two examples of simple harmonic oscillators, okay? We looked at a mass on a spring, and we looked at the pendulum. Now, what things affect the period of a mass on a spring? On a mass on a spring. You're right. Pendulum, yeah, length of the pendulum affects the period of a pendulum. What else affects the period of a pendulum? Now that we're on pendulums.
The mass. The angle is dropped.
No,
Ooh, I feel like we didn't get much out of that lab.
It was like the spring itself, or like the constant. I don't know.
Okay, we're back and forth between springs and pendulums. So the period of a pendulum is affected by the length of the pendulum,
The constant. Force of gravity.
gravity, not so much force, but the acceleration due to gravity. Remember, the formula is 2 pi times the square root of L over G. When we did that lab, your results should have indicated that angle of release, mass, had no effect on the period of the pendulum. Okay, if your lab did say that, you did the lab wrong. Okay, because they really should have had no effect whatsoever. Okay, all right, and then back to a mass on a spring, because that's what we started with. Mass on a spring, the two things that will affect the period of a mass on a spring are, this time you can say it,
the stiffness of the spring.
the spring constant, stiffness of the spring, and this time you can say it, mass. Yeah, this time mass does matter. Okay, so those are the two things that can affect the period of a mass on a spring. So the two formulas we went over were those two. Should you expect to see those on the exam?
Yes.
Yeah, they're on the front, on the formula sheet, but you're also going to have problems to solve with those. Okay? Is it important to understand what things affect the period of those for possibly a multiple choice question? Yes, definitely. Okay? All right, so definitely know those. Remember that if something is going to oscillate back and forth with simple harmonic motion, it does that because of a special kind of force called the restoring force. Okay, now, just having a restoring force does not guarantee that simple harmonic motion is going to occur. That restoring force has to vary linearly with displacement from equilibrium. Okay, and what symbol do we use for displacement in this unit? X, yeah. Okay, we use X for that. Okay, that's what you got to know about the principles of simple harmonic motion. Okay, and the problems that would require solving would be either a mass on a spring or a pendulum or both. Okay. Now, this part about the restoring force varying linearly with displacement was the discovery of whom? Hooke, exactly. Okay, so Hooke's law is the next thing that we got to know about. Okay, and Hooke's law says that the restoring force is equal to negative k times x for a spring. Or any other elastic object. Now, the way we talked about Hooke's law was in the same way that Hooke experimented on springs, and that was by hanging a mass from a vertical spring. Okay, and just seeing how far did the weight, okay, the force of gravity acting on that mass, stretch the spring, knowing that then the force in the spring and the force of gravity would be equal but opposite. Okay, does everyone follow me there? The example I gave you was the produce scale in the grocery store. Okay, if you use the produce scale in the grocery store, that's a Hooke's law device. Okay, there's a spring in there, and when you put the food in, okay, it pulls down and stretches. Gravity pulls the food down, stretches the spring, and the spring tells the dial how much tension is in it, and that gives you the mass equivalent of the items that you've put in the scale. Okay, your bathroom scale works exactly the same way. Okay, if you step on the scale says, "Get off!" Mine does. Okay, so if you step on the scale, you do the same thing. Okay, you compress the spring. Okay, the spring pushes back up. It's still gravity. It's just pushing instead of pulling. Okay, or sorry, the spring is pushing instead of pulling. Okay, and so you get again the same kind of reading. All right. So any Hooke's law problem solving that we did involved either the force in the spring being the net force. Okay, in which case negative k times x equaled m times a. Okay, so a Hooke's law question working like that would ask you about the acceleration of the object at a certain displacement, or would give you the acceleration of an object at a certain displacement and maybe ask you what the mass was or what the spring constant was or something like that. Okay, and the other way is the way that Hooke studied it. Okay, and that is that the force on the spring, okay, was equal to the force of gravity, and so we would have negative k times x equaled m times g. Okay, the thing about a Hooke's law question is it is only going to ask you about one point, okay, one single displacement. Right? If it's talking about comparing two places, it's talking about what kind of question? Conservation of energy, right? Okay, a Hooke's law question will simply say, what's the acceleration here? Or what's the mass of the object? Or something like it would only involve one point in the oscillation. Okay? A conservation of energy question must give you information about two and ask you to calculate something else. Usually it's going to ask you about speed or displacement. A conservation of energy question is never going to ask you for acceleration. All right, questions on Hooke's law. Okay, so expect, probably a couple of multiple choice questions around Hooke's law and probably a problem solving question, okay, to do with Hooke's law as well. Okay, and then we have law of conservation of energy. As we were progressing to the law of conservation of energy, we took Hooke's law and we showed how Hooke's law shows or can be used to calculate the amount of elastic potential energy an object might have. Okay, and so that would be this idea, that work is a change in energy. So it's kind of a work energy theorem thing where the work being done is being done by the restoring force over a distance, okay, and that would equal the change in potential energy. Well, spring force is, this would be actually average spring force, so we would have 1/2 times k times x times x, because that's what we use for d in this unit, and that equals 1/2 kx squared. So that formula is really restoring force, average restoring force times distance. Okay, that's where we get that from. All right, so conservation of energy in this unit could be one of two things. Could be a pendulum. Okay, could do law of conservation of energy with a pendulum. If so, it's just like the roller coaster questions from Unit 2. Okay, we would have EI equals EF. Okay, we would have EP initial plus EK initial equals EP final plus EK final. And for a pendulum, okay, that's going to be m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared, because a pendulum uses gravitational potential energy, not elastic potential energy. Okay. A mass on a spring, which is what you're more likely to get in this unit, okay, is going to have elastic potential energy. So everywhere where you see m times g times h, you're going to put in instead that. Okay. Does it work in principle any different? It doesn't. Okay, you're still going to manipulate and solve for whatever you don't have. All right. In a pendulum question, you can cancel all the masses. In a mass on a spring question, you can cancel all the halves. Okay, just kind of depends on how you want to look at it. Right? But in principle, they are exactly the same. The mechanical energy at one point equals the mechanical energy at the other point. Okay. With conservation of energy, we used some different terms. Okay, we identified things like amplitude, okay, as a term. Right, at the maximum amplitude of either a pendulum or a mass on a spring, the object would only have what kind of energy? Potential, because either the pendulum is as far from equilibrium as possible and thus not moving, okay, because gravity has slowed it down, or the mass on the spring is as far from equilibrium as it can possibly be, and the spring has slowed it down and stopped it, okay, for that instant. And then it's going to accelerate back towards equilibrium, okay? Both the pendulum and the mass on the spring are going to accelerate back towards equilibrium because there's a force acting on them, and forces cause acceleration. So they're going straight back to equilibrium. When they get to equilibrium, they only have kinetic. That's where their kinetic energy is at its maximum, okay? Where their speed is at its maximum, right? Making sense, everybody? All right, so those are the kind of things we have to remember. At the maximum amplitude, there's only potential. At equilibrium, there's only kinetic, okay? Where would the acceleration be the greatest?
When it starts going towards equilibrium.
When it starts actually moving towards equilibrium? Yes, because that would be at the maximum amplitude, right? Because as it passes through equilibrium, it's actually accelerating towards equilibrium, but it isn't moving that way, right? It doesn't start moving back towards equilibrium until it gets to its maximum amplitude, okay? At the maximum amplitude is the restoring force at its greatest. Yes, because x is at its greatest. Remember, Hooke's law says that the restoring force is equal to negative k times x. The bigger x gets, the bigger F gets. So when x is at its largest, that's when F is at its largest. And when A is at its largest. Okay, that's back to Newton's second law, right? The bigger the force, the greater the acceleration. All right, see how those ideas are tying together? All right, so probably expect, okay, a conservation of energy question. I don't think I will make it one where you would have all four kinds of energy. Okay, so it might be a little simpler than that. All right, questions on conservation of energy? Okay. Then we went to properties of waves. Okay. Most of the multiple choice is about waves and properties and behaviors of waves, right? And there's not that much multiple choice, and there's only like 14 multiple choice questions on this exam, right? The bulk of them are about waves, properties of waves, behavior of waves. So the definition of a wave is that it is a traveling disturbance. Okay? It carries energy, but not matter. It disturbs matter, okay? But it doesn't carry matter from one place to another. It carries the energy of the disturbance. Right? If a wave is going to travel, it requires a what? A medium, other than a light wave. Okay? It requires a medium in which to propagate. What are the two kinds of waves?
Transverse and longitudinal.
Right, transverse and longitudinal, okay, are our two types of waves. Right? So those are the kinds of things that could definitely, show up in a multiple choice question, okay, different kinds of waves, things like that. So in a transverse wave, which looks like this, okay, the disturbance is perpendicular to the direction the waves travel. In a longitudinal wave, okay, the disturbance is backwards and forwards, and the wave travels parallel to the disturbance. Okay, universal wave equation, is that important? Yeah, we used it in like basically every kind of wave question except Doppler effect. Okay, so it's definitely important to know the universal wave equation, which is V equals F times lambda or lambda over period. All right, so you would use that in an echo question. You could use it in a two-speaker question. You could use it in an error column question. Okay, any of those types of questions. All right. Now, the tricks that could happen with a universal wave equation could have something to do with this. How many waves are there?
3. 2.5. 3.5.
3. There are 3 waves here. Okay? So if I'm starting here, okay, that's 1 wave. That's, oh, sorry guys, you're right. 3.5, I drew 3.5 waves. I was trying to do that thing about the crests, and I went too far. I should have started at the crest. Okay, if there's 4 crests, if I just started on 1 crest and went to the 4th crest, how many waves would there be? 3. Sorry, bad diagram. Okay, remember that that's going to happen. That's going to come up. I guarantee it. All right. So if somebody's, in the ocean on a boat and they count 5 crests, that's how many waves? 4. Just remember that. Okay, it's probably something that could come up. All right. Yeah. That's about it for a wave equation by itself. Okay, there's not going to be a lot for a universal wave equation by itself, but there probably is one thing. Okay, but then you have to use universal wave equation for lots of other things. Okay, echo questions, standing waves, two-speaker questions, those kind of things. Okay, for an echo, what's the trick with an echo?
The sound travels there and back.
Right, the sound travels there and back. So if it tells you they hear the echo after 4 seconds, it only took how long to get to the wall?
2 seconds.
Right, just little things like that, little tricks that we have to remember. Okay, okay, interference. So there's a few different ways I'm going to talk about or ask about interference on the unit exam. One of them I spoiled for you before Christmas, but I'll spoil it again. Okay, I give you a diagram and I say, this. These 2 waves are occupying the same space at the same time in a medium. What type of interference is occurring, and draw the resulting shape of the medium. All right, what kind of interference is occurring?
Construction.
Constructive, how do we know that?
Because they're crest and trough.
Right, they line up. They're what we call in phase. I might use that terminology on the exam. Okay, if they're in phase, it means they look like this. If they're out of phase, it means when one is up, the other is down. Okay, so these are in phase and will interfere constructively. Okay, let's say this one has an amplitude of +1 and this one has an amplitude of +2, +3, and -3. Boom, resulting waveform. 3 marks. Okay, 1 mark for the correct type of interference and 2 marks for the diagram. All right, and the other way I might ask about interference, 2-speaker question. Okay, so if we have a 2-speaker question, the observer will be directly in front of one of the 2 speakers, because that's the way we did them. Okay, what determines whether this person hears a loud sound or a quiet sound?
If the waves are constructive or destructive.
Okay, and how do I know whether they're going to be interfering constructively or destructively? Because they're getting waves coming to them from 2 sources. Okay? If those waves are in phase, I'll get constructive interference. I'll hear a loud sound. If they're out of phase, I won't hear anything. Okay? But how do I know whether I'm going to hear anything or hear nothing?
If the waves match up, isn't it deconstructed and you hear nothing at that particular point?
Yes. How do I know that's what they're going to do?
But, like the amount of wavelengths.
Right, it's the number of wavelengths from each source that determines whether they meet up in phase or out of phase. Okay, so if I know this distance and this distance, okay, then I can calculate using the wavelength how many waves there are. So let's say that from this speaker to the person, there are 3.5 wavelengths. And from this speaker to the person, there are 1.5 wavelengths. Does that person hear a loud sound or a quiet sound?
Wow.
Loud. Okay, that person hears a loud sound because if I subtract I get a whole number of wavelengths. That means they are going to arrive at the same point in the wave. So this would be 1 wavelength, 2 wavelengths, 3 wavelengths, and a half. Okay, and this would be 1 wavelength and a half. They are arriving crest to crest, trough to trough, interfering constructively.
So just to clarify, if you were to subtract them and you got, say, like 2.5, it would be destructive and they wouldn't hear it.
Right.
Okay.
Yeah, because then one would be arriving at a half wavelength, one would be arriving at a full wavelength, and they wouldn't match up. Okay? Should you expect a 2-speaker question?
Yes.
I would. Sorry, did anyone need that before I moved up? Okay, waves at a boundary. So this is going to be more multiple choice kind of stuff, but like what happens when a wave enters a new medium or crosses a boundary between one medium and another? Okay, so what property of a wave never changes when that happens?
Frequency.
Okay, can everything else change?
Yes.
Absolutely. Speed, amplitude, wavelength, direction, all of those things can change when a wave crosses from one medium to another across a boundary. Yeah. Other things we have to know. What happens to waves when they hit a boundary?
Reflection.
There's some reflection and some transmission. Okay, will we need to know the relationship between whether it's going into a faster medium and the nature of the reflected wave? Yes. Okay, if it's going into a faster medium, the reflection will be upright or inverted? Upright. Okay, if it's going into a faster medium, that's easy. It goes in easily. Very little energy gets reflected back, and it gets reflected back. Upright. If it's going into a more dense medium, that's harder. It's more difficult to cross the boundary. The reflection is inverted. Okay, everyone following me there? Okay, if it goes into a faster medium, what happens to the wavelength? It will get
Oh, bigger.
bigger, okay? Speed and wavelength do the same thing. That's how frequency remains the same. Okay, so if the wavelength gets longer, it's because the front of the wave ran away from the back because it was going faster than the back of the wave. Making sense? Okay, if it's going into a slower medium, it gets jammed up and the back of the wave catches up. Okay, that means the wavelength will decrease because the speed decreased. And in that situation, what's likely to happen to the amplitude? It'll go up, maybe. Okay, some of the energy might get lost at the boundary and maybe the amplitude doesn't change very much. Okay, but most of the time we would generally see, because the wave is being compressed, that it's going to go up. Okay, like a tidal wave, right? That's why tidal waves rear up when they get close to shore. All right, so definitely review that stuff. That is memorization. Like you do just have to memorize what happens in those different situations. Okay, that's going to be a diagram type of question. Okay, there'll be actually lots of diagrams in the multiple choice, and then you have to determine, okay, faster, slower, okay, based on what you see in the picture. Okay, then we talked about standing waves. Okay, that was starting on Monday. We started with standing waves. Okay, and you'll need to know your terminology. You'll need to know, nodes, antinodes, fundamental, first harmonic, second harmonic, third harmonic. Okay, be able to identify those in a picture. And so if I show you a picture that's got 3 antinodes, you would know that would be the third harmonic frequency. Okay, things like that. Okay, something else I might ask. So let's say I put something like this on there. Okay, so it's got that standing wave pattern on it. The string is 6 meters long. What's the wavelength? Four meters. Yeah. Okay, so here's how we would figure that out. You could do it if you're like a really good visual processing person. Okay, you could go, this is 6 meters, so that would be 2, 4, 6. Oh, so that's one wavelength right there. That would be 4 meters. If you're a visual person, you could do it that way. If you want to do it mathematically, you can say 6 meters equals 1.5 wavelengths, because there's 1.5 waves on that string. Okay, and then divide 6 by 1.5, you will also get 4. Okay, either way. Okay, and I could have a follow-up question to that. I could say, if the frequency being used to generate these waves is X number of hertz, calculate the speed. Could you do that?
Yes.
Yeah, because you'd know the wavelength is 4, and you'd have the frequency, and you'd plug it into the universal wave equation, okay, and have it there. Okay, so those are all kind of simple standing wave kinds of questions, and I would say that that's probably not something that would be a written response question. Because what do you have to do? Figure out one number, okay, maybe 2. All right, and then we talked about air columns after that. Okay, so open and closed. Okay. So for a closed air column, at its fundamental frequency, 1/4 of a wavelength is inside of the tube. Okay, that's why we have the formula lambda equals 4L. And for an open air column, at its fundamental frequency, there's half a wavelength in the tube. That's why we have lambda equals 2L. So it'd be very easy for me to give you a question about an air column and ask you to calculate like what the fundamental frequency would be and give you the length and the speed, okay? Or give you the length and the frequency and ask you to calculate the speed of sound, okay? Things like that, right? It's always gonna be the same thing. You're gonna use one of those two formulas and the universal wave equation, okay? Other thing to remember, because I did spoil this before Christmas, and I'll remind you about this spoiler. Okay? There could be a part B where you might be asked what another frequency that could be produced by that tube would be. Okay? So if you know what the fundamental frequency is, could you calculate other frequencies? Okay? So if I asked you what the next frequency you would hear would be for an open air column, what would it be?
It would be 2.
Yeah, it'd be 2 times the fundamental. What would be the next one you'd hear for a closed air column? 3. Right, because remember, closed air columns only resonate at every other harmonic frequency, because at F2, you have a node at the top. Okay? F2 for this one makes a sound. Okay? Questions on the air columns? And then lastly, Doppler effect. Right, which we've gone over the last couple of days. There's nothing terribly complex about the Doppler effect. Okay? You know I'm really going to only ask you for one of 3 things, and that would be either F, FO, or the speed of the source. Is that a good one for me to work this formula into? Okay. How do you know if you have to use that formula?
As soon as you do the temperature.
Yeah, if I give you a temperature, you have to use that formula. Okay? And that would be the only way you'd get the speed of the waves, the speed of sound in particular, okay, for that particular
And that
question.
speed of sound formula will be on the front sheet.
It is on the formula sheet, yeah, it's on the front of the test.
Will you always put the temperature in Celsius or? will you-
Oh, yeah, definitely, because that formula really only works for Celsius.
I know, but I thought you would like put in Fahrenheit, and you'd have to calculate for Celsius and
You really don't think much of me, do you? Okay. As long as we know where we stand with each other. I would not do that to you. I don't know how to convert Fahrenheit to Celsius. I'm no good at that, so I wouldn't do it. Celsius only. We're in Canada and we use the metric system, as people should. Yeah. Okay, and I won't put it in Kelvin either. Okay, it doesn't work in Kelvin. You have to, add 273 or whatever it is. Okay, won't do that either. That's it. That's what's on there. Okay, those concepts. Okay, so as I said, there are 14 multiple choice questions. Okay, and they ask about the nature of waves, okay, wave behavior at a boundary, lots of diagrams, okay, yeah, properties of waves, more properties of waves. There's only three questions out of the 14 that are on simple harmonic motion. 11 are on waves. Okay, and then in your written response, you have an interference question, an error column question, a wave behavior question, the simple harmonic motion question, conservation of energy question, a simple harmonic motion question, a Hooke's law question, a Doppler question, and an interference question. So there are 9 written response problems. Okay, but there are 9 written response problems because the multiple choice should realistically take you 5 to 10 minutes. Okay, like with the multiple choice, you either know the answer right away or you're probably not gonna get it. Okay, yeah, there's really only about 3 multiple choice questions that you might have to actually look at and go, think about it for about 30 seconds. Okay, the other ones will be pretty straightforward. Okay, and like I said, lots of pictures in multiple choice. Okay, so that test is going to be out of 61 marks, so it's pretty much on par with your other ones. Okay, anything you would like me to cover in more detail? Or go over?
You said wave, you said that there was a written response for wave behavior, what was that going to?
I said it was a written response question about wave behavior?
Yeah.
Multiple choice questions about wave behavior. Okay, yeah, sorry, wave behavior. So that would be like when I was telling you, a person's on a wave, right? And they count this many crests, like, okay, or an echo question, or that would be a wave behavior problem because you'd have to use the universal wave equation or something like that. It's still a behavior of waves question, but it's not a, like, what is it going to be upright or inverted kind of question. Kind of like that.
Can we go over another interference question? Do you have
Like the diagram or the 2 speakers?
the diagram? Or either one? Sweet.
There's a 2 speaker question.
That works.
Okay. But we can really quickly do a diagram question. So,
Whichever one's on the test.
well, I already did one. So if you want to see what the other, like, oh, that's terrible, that diagram. Let's just pretend it's not terrible. We can't even pretend. Should have drawn that line first. Constructive or destructive?
Destructive.
Okay, what's my resulting waveform gonna look like?
It's gonna be small.
I would have like grid lines on that question so you'd know exactly what the answer, you wouldn't have to guess. Okay, but that means also you have to draw it exactly on the right lines. Okay. All right, try the 2 speaker question. Okay, worth going over. All right, so in this question we got these 2 speakers, okay, and they are 2.815 meters apart. Okay, they are emitting tones of 523 hertz in a room where the speed of sound is 340 meters per second. The observer is directly in front of one speaker, 1.625 meters. Okay, so that's the point right there that we are being asked about. This person's head is floating off of their body. There we go. Okay, so we want to know whether that person hears a loud or quiet sound, and that is based on how many wavelengths travel there from each speaker. Right now, I'm missing 2 vital pieces of information. What are they?
The distance in between the second speaker and the person?
Right, I need to know this distance right here, so a simple Pythagorean theorem calculation will get that for me. So 1.625 squared plus 2.815 squared. All right, so that's going to be 3.25 meters. Okay, what's the other vital piece of information? Wavelength. Okay, so I can get that with the universal wave equation. Lambda will equal V over F. Okay, so 340 divided by 523. All right, is 0.65 meters. All right, so those are my pieces of information. Now that I know the wavelength, I can figure out how many wavelengths there are between this speaker and the observer, okay, and this speaker and the observer, simply by dividing the distance by the wavelength. That'll tell me the number of waves. Okay, so I take my 1.625 and I divide it by that number there. Okay, so I get 2.5 wavelengths. All right, then I'm going to do the same thing with this side. I'm going to take that number I calculated right up here with all the decimals, okay, and I'm going to divide that by the wavelength I calculated with all the decimals. All right, and that's giving me 5 wavelengths. Okay, 5 minus 2.5 is 2.5 wavelengths. Does that person hear a loud sound or a quiet sound? Quiet, yeah. Okay, that is destructive interference. Okay, questions on that one?
How do you know if it's destructive?
If I get a half a wavelength difference, when I do that subtraction operation, if it comes out to something 0.5, it's destructive. Okay, because like this one went 5, so it's arriving as a crest. This one went 2.5, that's arriving at the opposite part of the wave as a trough.
If they both arrive at 0.5.
Then it's fine, they'll both arrive as a trough,
Oh.
right? And then when I subtract the 2, I'll get a whole number. As long as, if I get a whole number, it's constructive. If I get 0.5, it's destructive. I won't be a jerk and make it 0.3. Okay, because, well, then you're gonna go, it's kinda. Yeah, and that's, you need a concrete answer. All right, now, obviously, with this question, the answer, the final answer is loud or quiet. And it's a 5 or 6 mark question. Are you gonna get 6 marks if you write loud and are right? No. Okay, I will give you 1 mark and say, nice guess. Okay, you have to have proof of your answer. Okay, I'm not giving you 6 marks for a coin flip. Okay, that's not cool. You gotta have some proof there. Okay?
It's something you would do.
What?
Noah would just write quiet.
Quiet. And the kind of thing I would do would be, right, good guess. Yeah.
It's a 50-50.
It's a 50-50 chance.
I'm getting 1 out of 6.
Now, if you had a vector addition question from Unit 1 and you actually guessed the right answer with no proof, I would give you 8 marks. Because the chances of you guessing the correct solution to a vector addition problem are astronomical. And you would deserve 8 marks for being that good a guesser. But not in this case. Okay, what else do we want to go over? Or we want to just see what else Coderre has on the magic board?
Can we go over some pendulum questions?
Come on, pendulum question. No pendulum question. Okay, I gotta make up a pendulum question. Okay.
Yeah, go ahead.
Okay, there would be a pendulum question. Difficult. So we're just looking for length. Okay, so we're looking for L. We know the period is 1.35 seconds, and we know that because we're on Earth, it's 9.81 for G. So T equals 2 pi times the square root of L over G. I'm looking for something that's under the root, so I have to square everything before I can start manipulating. So T squared equals 4 pi squared times L over G. Then I multiply both sides by G and divide both sides by 4 pi squared. Okay, to get L, so 1.35 squared times 9.81 divided by 4 pi squared. All right, so it'll be 0.45 meters, 0.453 meters long. All right, everybody okay with that? Okay, what else would we like to try? Or do you guys just want to work on the review sheet?
Is there a conservation of energy?
There is a conservation of energy question in there somewhere. That one. That's a law of conservation of energy question. Okay, so on this one here, okay, we got mass on a spring. We know what K is, and it's oscillating with simple harmonic motion. Its maximum amplitude is 0.65 meters. All right, so that's an important thing to know. Okay, amplitude is 0.65 meters. K is also an important thing for us to know. 2.5. 2.5 newtons per meter. Okay, we're looking for how fast it's moving when it is 0.2, so we need to know VF. Okay, when its final displacement, which is XF, is 0.22 meters from equilibrium. All right, so my initial point is going to be the maximum amplitude. How fast is the object going there?
0.
0. Okay, so I'm going to set this up as a law of conservation of energy question, EI equals EF, knowing that my initial energy is all potential. And that at the end, I have a little bit of both. Okay, because I'm not at equilibrium at the end. Okay. So I am looking for how fast it's going, which is part of the kinetic energy final. So I want to subtract the final potential over to the other side before I start putting in any formulas. Okay, at this point I'll put in the formulas, okay, and I'll say 1/2 Ka squared minus, and that'll be like initial, minus 1/2 Kxf squared equals 1/2 mvf squared. Okay, halves in every term, so I'm going to get rid of it. I'm trying to find vf, so I'm going to divide both sides by m, and I didn't write what m was down. What's it? 1.5 kilograms. Okay, and so when I do my manipulation, that's what it's going to look like. Okay, square root of mass times, oh, that must have been for another question. That's not right. Okay, so I've got my Ka squared here. Sorry, that was K. That was right. Whoops. Undo. There we go. Okay, so this is K. K times my amplitude minus K times my second displacement divided by the mass, square rooted, should give me 0.79 meters per second. Okay. Everybody all right with that? Okay. I would expect one like that, or maybe even a little tiny bit easier than that, okay, on your unit exam. All right, what else would we like to look at? Oh, no tubes, okay. I will make one up. Okay, so for this one here, okay, we know the length, okay, is 1.2 meters, and we know the temperature, which we're going to use to get our speed of sound, so 332 plus 0.6 times 14. All right, 340.4. Okay, so I'm looking for the frequency. To get frequency, I'm going to need V and lambda. But I can get lambda because this is an open air column where lambda is 2 times the length of the tube. Okay, so lambda equals 2.4. So I'm going to take my 340.4 and divide by 2.4. All right, so I'm getting that the frequency for that sound is 141.8. Well, we only have 2 significant digits there. So 1.4 times 10 to the 2 hertz. Okay, now if it were me, I would probably ask a part B. What's the third frequency produced by this tube?
It would be 2.
4.2 should be 4.2 times 10 to the 2 hertz.
It would just be 1.4.
4.3, because we'd have to round it up.
But it's an open air column, so wouldn't it be?
But I said the third.
Oh.
The third frequency you would hear. Okay, third frequency you would hear for this one would be F3. Third frequency you would hear for a closed air column would be F5. Okay. All right. Any other ones? Everybody's good? Okay. I'm sure I got something here worth looking at. There you go. There's a wave behavior problem. So we're looking for acceleration. Okay, we know that the spring constant is 3.5 newtons per meter. Okay, we know the mass is 0.85 kilograms. Okay, and we know that it is 0.38 meters from equilibrium. All right, so in this case, the only force acting is the spring force. Okay, that makes it the net force, which makes K times X equal M times A. In this case, they give me no vectors, so I'm not even going to bother to put them in, because I can't give a vector on this acceleration without a vector on the displacement. And they didn't say the displacement was 0.38 meters left of equilibrium, then I could say the acceleration would be right of equilibrium, but I can't. Okay? In this case, I could just give the magnitude of the acceleration, and it would, I could give this direction, towards equilibrium. That's the best I could do. Okay? So, I'm looking for acceleration. I'm just going to divide both sides by mass, okay? And then I'm going to put in my numbers. So 3.5 times 0.38 divided by 0.85. All right, so my acceleration would be 1.6 meters per second squared towards equilibrium. Best I could do.
If we ever had something where we weren't given like a vector in this situation, would you expect towards equilibrium?
That would be the one you could put on there, and thus I would expect it.
Okay.
Yeah. Okay? Because restoring force and its resultant acceleration is always trying to restore equilibrium. So if you are given nothing else, like left or right, go with that. Okay? Any other ones?
What's the worst type of question on this test?
There really isn't. On this one, it's all about the same, usually. I don't usually have one question that goes significantly worse than the others. Open air column?
Sure, why not?